as we look at Mona Lisa, our eyes jump from one point of interest to the next in the scene, and as we fix our gaze on any particular feature, Mona Lisa's smile here, what happens is that photons of, and they're going to be hitting our eyeballs and enter through going through the various retinal layers. Video is a little bit slow, I apologize, but until eventually photons hit the photoreceptor layer, which we see here at the back of the eye with the three types of cones. And these light signals get transduced into electrical signals, which then travel out of the eye, out of the retina, via the optic nerve. You see the signals living there as a red dots, and that's the optic nerve. We have the two eyes labeled with two different colors. We see the signals decussating at the level of the optic chiasm, the crisscrossing, reaching the lateral geniculate nucleus in the visual thalamus, which is sort of a relay station, and then we travel via the optic radiations to the primary visual cortex here in the back of the brain, which is where the signals from the left and the right eye mixing for the first time. All right, so what does this mean for our everyday vision and perception? Well, the first thing that we need to know when we explore a visual scene, I mentioned that we're making eye jumps and we eventually fix our eyes on a particular detail. So we do this 2 to 5 times a second, every day, every hour of the day. In fact, during our waking hours, we make some 200,000 saccadic eye motions, these little eye jumps, and that, 200,000 a day, of which we're only making on purpose or are even conscious of just the tiniest portion, maybe a couple of dozen eye movements a day we're conscious of. The rest is pretty automatized. Now, what does it mean to look at something? To look at something means that we're pointing the high resolution area of our retina, this is called the fovea, where our photoreceptor density is highest, we're pointing it to that location in space. That is what it means to look at something, and when we look at something else, we point our fovea elsewhere. Now, it's important to realize that that's the only place where we have high resolution vision that's equivalent to the width of your thumb at arm's length. That's the extent of the fovea. So we, however, experience a grand illusion all the time, which is that we see the whole world in high detail, when in reality, except for that tiny portion, that's where we can thread a needle, that's where we can read. Everywhere else, we're basically a blur. We're legally blind everywhere else than that tiny portion. All right, so it is eye movements that give us the impression that build this simulation that we can see everything at once in high resolution, which is not true, right? So the visual system and the oculomotor system working together, they're grabbing snippets of information and they're stitching together a whole visual scene. So this is what our perception looks like. In reality, at any given time, is much more like that. And as we shift our eyes from one point of interest to the next, this is what the actual retinal input. Now I'm going to show you the eye movements like in real time that somebody would make looking at this same scene. We call these scan paths. So you can follow the black path. When there's a gap, that means that there's a blink. And you can see that we're looking at interesting parts of the visual scene. Clearly, the visual system cares about faces and presence. Um, and, uh, and yeah, and it is through these eye movements that we think we perceive the whole scene. Realize that there are whole areas of the visual scene where our eye doesn't land even once, but we still think that we can see everything. All right. So let's go back to our animation and what happens when we look at a visual scene. So now we know that these eye jumps are called saccades. They direct our fovea to one point of interest to the next over the visual scene. But even when we think that we're looking at something specific, that our eyes are rested on some region of interest, the fact that it is not true, our eyes are never at full rest because we produce so-called fixational eye movements. Now, again, this is worth reiterating that our eyes are never still, even during visual fixation, even when we think our gaze, we're holding our gaze as precisely as we can, we're still making little eye movements. And if these eye movements are eliminated, and that can be done in a number of ways in the laboratory, visual perception goes away. It fades almost instantly. All right, so these tiny movements are critical to our perception. In fact, as we explore a visual scene, those periods of quote unquote fixation, so we never have actual fixation, but it's sort of attempted fixation, if you will, these periods of attempted fixation amount to about 70-80% of our visual exploration time. We've measured this in our lab. So fixation or eye movements drive, in fact, a lot of our vision during fixation, but also during exploration. And we're going to see a lot more through this presentation about how fixation and exploration are related and how they integrate with each other. All right, so I have told you that we're constantly making these little eye movements, but this may seem hard to believe. We're going to convince ourselves, we're going to prove it to ourselves that these eye movements exist. And to do that, I need you to look at the very center of this screen, look at the black dot, and don't look at me, keep looking at the black dot, because you need to hold your eyes there for the next 40 seconds, trying to keep your gaze as still as you can on the black dot, because what we are trying to do right now is we're trying to generate a very powerful after image of this pattern. So when I tell you, which is not yet, but when I tell you, I'm going to ask you to take your after image of the grid and center it on the white dot. And let's do it right now. Take your after image, center one of the crosses over the white dot, keep it still, don't move the cross, keep it as still as possible, don't let it move. It's impossible. So that's what's happening in your vision all the time. You think that the world is stable, but your retinal input is shifting constantly, and those motions are the motions that your own eye is producing all the time. Those are your fixational eye movements. Now, I mentioned that there are a number of ways to remove fixational eye movements and all eye movements in the lab. So this is one of the early ones, which is it's easy to think about. We don't do it anymore because, as I understand, it hurts a lot, for one. But what you see here is an eyeball that has a visual target that is physically attached to the eyeball by means of a suction mechanism. So when you move the eye, the target physically moves with the eye. You have no net motion. This target is going to disappear right away, because the fact is we need things to change in order to perceive them. Otherwise, our neurons adapt and you stop seeing. So going back to the animation, here we have our subject now looking at the same picture, but now the picture is that tiny square that is physically attached to his eyes. So when he tries to explore the image with his gaze, the image moves with the eye, is retinally stabilized, and that means that it's going to fade away almost instantly. So that's a pretty heroic approach to retinal stabilization. This is even more heroic. So this is Stevens, I think, from 1970. You can tell it's from the 70s from his mustache and hair. So anyway, so he wanted to stabilize his eye movements. He wanted to remove his eye movements, and so what he did. This is an image from his paper. He completely paralyzed himself. So the image is not even as dramatic as it may be, because he was being artificially ventilated because he couldn't move his lungs, he couldn't move his chest during the experiment. He could only move one part of his body, which was his fingertips on one hand. He had a tourniquet applied to one of his arms to disrupt blood flow to his fingertips so he could move his fingers and report on his perception during the experiments. Yeah, the paper is worth taking a look at, but as the paper establishes, visual fading became a real problem during these experiments. Don't try that at home. All right, so without going as far as these pioneers, we can actually get a feeling for what retinal stabilization looks like just by exerting a little bit, not a whole lot, but a little bit of volitional control over our own eye movements. Now, hopefully everybody can see on this image a red dot surrounded by a blue ring. Everybody sees the blue ring? Okay, very good. So now, fix your gaze as precisely as you can on the red dot and keep it there. And just in a few seconds, it's happening for me. The blue ring should start to fade away. It's important that you don't look at the ring to see if it's still there, because you're going to bring it back. Look at the red dot, and portions of the ring will start to disappear. And if you keep your gaze stable enough, you should see at some point that the red dot is completely surrounded by a blank field, right? So you can see how with just a small amount of control on your oculomotor behavior, you can have a pretty dramatic effect on your perception. All right. And this, of course, applies not just in the laboratory, but outside in the world, in nature. There's a cat hiding here in the tall grass. If you pick one of the dots on the tree and fix your gaze there, you can see that in just a few seconds, the cat should merge pretty seamlessly in the tall grass and becomes virtually invisible. All right, and we will get back to this concept. All right, so of these fixational eye movements that I mentioned, well, there are three types called microsaccades, drifts, and tremor. So microsaccades, as their name indicates, they're small saccades. So they're about 1 degree or smaller, 1 degree or less of visual angle. Now, 1 degree of visual angle, again, that's the extent of your fovea, is your thumbnail at arm's length. So that's how big microsaccades are at their biggest. They tend to be quite a bit smaller, but they are the fastest and the largest of the three types of these microscopic fixational eye movements. So we started studying microsaccades a couple of decades ago, and that we were attracted to them for a number of reasons, and that something that was intriguing about them was that people used to think that they were sort of like nervous tics of the eyes, that they had no useful purpose. But we thought that they might be involved in troxler fading because, as you've experienced for yourselves, when you try to keep your eyes still, visual fading happens. And so that when you're trying to keep your eyes still, what you're actually doing is you're suppressing your microsaccade production. So we hypothesize that microsaccades should be important to recovering faded vision. And if that was true, if microsaccades counteracted fading, we should expect to see more microsaccades before a target becomes visible, and fewer microsaccades before the target becomes invisible. And that's exactly what we found. So, okay, so here we're looking at time around the moment. 0 is when the subject in the laboratory indicates that a visual target, so the people, the subjects are fixating on a fixation target, and they're also paying attention, like you have done, to the blue ring. They had a different stimulus, but it doesn't matter. It's the same idea. They're fixating their gaze, and they're reporting on their perception of a fading stimulus. We designed the fading stimulus so that it would be faded and invisible roughly 50% of the time. And so people are pressing a button or releasing a button to indicate when it's faded, when it comes back, and so on. Okay, so that happens at 0. And what we're looking at in this red line, this is the microsecond rate before the stimulus becomes visible at 0, okay? So you can see that about a couple of hundred milliseconds before the stimulus becomes visible, we have a peak in microsecond rate. Conversely, before the stimulus becomes perceptually invisible, we have a drop in microsecond rate. Okay, so this was the first indication that microseconds were relevant to our perceptual experience, and we did a number of follow-up experiments to show that this is a causal relationship and not just a correlation. Interestingly, because these subjects were naive and we didn't tell them, we just asked them to indicate when something was fading or intensifying perceptually, a number of people actually thought that it was the physical stimulus that it was changing, becoming brighter and dimmer. They didn't realize that it was their own eye movement behavior that was driving the changes. The stimulus itself never physically changed. All right, so more recently, we have applied similar concepts to some art perception. And this is one of the paintings that we have been studying. So this is Monet's Impression Sunrise, which is the painting that gave its name to Impressionism. Now, the painting here has a little tiny difference from what the way Monet painted it, which is that we have a little red dot on the head of the sailor, and that was for people during the experiments in the lab to fix their gaze. We were asking them to indicate when the sun was fading or intensifying, because something that is very interesting about the sun in this painting, and this has been reported by Margaret Livingstone and other people, is that the sun is equiluminant. So that means that even though the sun, there's a lot of chromatic contrast between the sun and the surrounding sky, there is no luminance contrast. If we looked at this image in black and white, the sun would be practically indistinguishable from the sky. So I want you to, hopefully this projector will collaborate. I want you to fixate on the head of the sailor as precisely as you can. And what should happen is that the sun is going to disappear in terms of, yeah, a good fixation. And if you relax your eyes or you blink, the sun will come right back. Okay, so this really suggested that what's happening in this painting is an example of Troxler fading. Troxler, we call this type of fading after, it's named after the philosopher who popularized it in the 1800s. All right, so we actually, we thought that we actually knew what was happening just by doing the exercise you all have done, but we do actually have data. And that the experimental design was very simple. We have a stimulus that doesn't change. This is not to scale, but you get the idea. So the stimulus never changes. The perception does, depending on how well people are fixating or if their gaze gets tired or whatnot. And they have to indicate pressing or releasing a button, what their perception is. And we have the same graph. So here, this is with a Gabor patch. This is the original experiment that we did with a contrived stimulus. So this is the original, sort of like the original data that I, or with the original stimulus that I showed you previously. Now this is with Monet's painting. And you can see that we have the same type of relationship with microsaccades being responsible for the alternations in perception. All right, so I want to switch gears slightly and go from perception and fading to attention. And I want to start by showing you an illusion by Peter C. And this illusion actually allows you to visualize your attentional spotlight. So, so we have three circles, sort of a Venn diagram. I want you to look at the center, but you don't need to be very compulsive about your fixation here. You can just look at the at the orange dot normally. But what I want you to do, or no, not orange. Mm. Mm. All right, orange or yellow dot. Please look at it, but pay attention to, say, the upper right circle without moving your gaze from the center. You should see that the upper right circle becomes brighter, more salient. It looks like it's on top of the other two circles. Now let's do the same with the upper left circle. Keep looking at the central dot. Now the upper left circle becomes brighter and more salient. Now let's try it with the lower circle. Now do it with your own free will, if you still think you have any. And whichever circle you choose to pay attention to, it becomes brighter and it becomes sort of like overlapping the other two. Nothing is changing in the image. I'm not controlling your eye movements, or so you think. But, it's just your own attentional spotlight. Now, and this is what happens all the time when you pay attention to anything in the world, whatever you're paying attention to becomes more salient and everything else less so. We don't have time to get into that research right now, but it's worth mentioning that even though the attention spotlight metaphor is a useful one, the way that attention works is actually not by enhancing your perception. What paying attention means is that you're blocking everything else in the world via inhibitory synapses. You are suppressing everything else. That's why what you pay attention to seems brighter and more salient, but that's actually sort of an illusion. All right. So I wanted to introduce the concept of attention because we're gonna get back to Yarbos. So Yarbos, I think I forgot to mention his name previously, but he was responsible for the retinal stabilization experiments that I mentioned at the beginning with the target physically attached to the eye. Now, that's actually not what Yarbos is most famous for. What Yarbos became most renowned for was because he brought cognition to vision, so to speak. Now, this is a painting. It's called The Unexpected Visitor, I believe. And Yarbus famously had people look at the painting in the laboratory and collected the scan paths as they observed the painting, in this case, as you would in a museum. Now, the most interesting thing, though, was that he then gave people different tasks, different ways of looking at the painting. And so here we have different scan paths, all from the same participant doing different things with the painting. So in one of the scan paths, he's looking at the painting just normally, as you would at a museum again, or in a different scan path, they're trying to estimate the ages of the different people, or they're trying to figure out how they're related to each other, which of them are family members, or they're trying to estimate if the family is rich or poor based on their belongings. So with the same image, you have all different ways of oculomotor patterns that go with it. So we have both what we call bottom-up and top-down influences on how we look at a visual scene. And what Yarbos did at the macroscopic level, we can actually also do at the microscopic level, looking at fixational eye movements. So this is data from my lab. We have here a natural scene, some children with some props, the scan paths that go with it, sort of like Yarbos would collect the scan paths. But now we can go into more detail and actually at each fixation site, we can see what's going on, where the microsaccades happen, where they drift in between microsaccades, and so on. Now you can see it's maybe you don't see so well from the back, but what I want to bring your attention to is that not all fixations contain microsaccades, but those fixations that happen over the children's faces, those do contain microsaccades, and that we're gonna keep addressing this issue about how microsaccades seem to be important for extracting information from places in the visual scene that we care about, or information-rich places that are informative for whatever reason. Okay, and of course we can use these same techniques to try to understand visual search better. And one of the first things that we did was to look for Waldo. So you are probably all familiar with the children's books. So Waldo is here inside of the blue square, and I have to mark it because otherwise I lose him. And so people are trying to look for Waldo and the other characters in the laboratory while we measure their eye movements. And now what's interesting about this kind of scene is that it's very crowded. There's a lot going on, and that it's almost like a texture. And uh, and so basically what it means is that unlike the regular natural scenes where we had like faces are more interesting than non-faces to the visual system, objects than non-objects, and so forth. Here everything is sort of a mess, so we don't really have a lot of bottom-up features to guide us. All that we have is our task, top-down task of looking for Waldo. So how does the oculomotor system deal with that, and what happens with microsaccades? So again, we see here the scan paths in real time. Black lines are large saccades, red little lines are microsaccades. There, we have Waldo, we have a whole bunch of microsaccades to go with it. Notice that not every fixation contains microsaccades. Participant is still looking for the other characters. I think there's a wizard and I forget what else. But in a moment, they're gonna try and come back and see that Waldo hasn't moved, and we're gonna have the microsaccades to prove it. So okay, you missed it, uh, but they'll be back. They'll be back, and as they confirm and reconfirm that Waldo is still there, now we have again increased microsaccade production. So you can already see this qualitatively, and of course we can quantify it, and in this um, project we actually looked at fixation consistency across observers. So we had different people look at the same images, and there were areas, there tend to be areas in which most of us would fixate looking at a visual scene, which we call the regions that are consistently fixated across observers. Again, faces are going to be some of these prominent regions, objects versus background, etc. And the gray part is labeled as regions of the scene that are inconsistently fixated across observers. Some people look at it, other people didn't, so it varied. Again, notice that if we look at the scan paths of one individual subject over the consistently versus inconsistently fixated regions, that's where the microsaccades tend to relate. It's not a perfect match, but by far you have the most microsaccade production in consistently fixated regions, which are the informative regions of the scene. Now, I'm saying that these regions are informative from an agnostic perspective. We don't know what bottom up or top down factors are making these regions informative, but we know that they're informative because those are the regions that subject after subject fixate consistently. All right. So this is good. This is all fun and games so far. Looking for Waldo and whatnot, but it also has real world applications that are quite critical. So this is a graph from about 10 years ago about the causes of death in the US. So we have a non-insignificant contribution from medical error. That's about a 5% contributor to causes of death. And what's interesting is that this percentage has stayed still for the last 50 years, even though there has been an explosion in imaging technology, the way that we can acquire imaging data right now with the resolution and variety and so forth and modalities in the last 50 years is like day and night, but the human brain has not changed, and so the medical error remains constant. Uh, I guess I said 5% is 4%, but still, this leads to 40 million errors per year. So what can we do to address? So first off, why this error, and what can we do to address it? Well, this is ongoing work, but we have some hints, which is it may have first off something to do with how people get trained, in this case, to become an expert radiologist. So radiology residents, they get trained to look for abnormalities in tissue. Here, this would be in lung tissue. So they're looking for abnormalities in these two lungs. They're looking for nodules, and they're taught to do it in a very stereotyped pattern, following this zigzagging pattern, top to bottom, one lung, then the other lung, and then just looking across the two lungs for asymmetries. Okay, so that's the theory. This is what expert radiologists do in reality. So nothing to do with the way they're supposed to do it. Now the nodule is down here, indicated by the arrow, and these two experts successfully found the nodule, but they did it in a very idiosyncratic, very individual way. Okay, so we know that somehow people arrive to a radiology residency program. By the end of it, they know how to look at medical images, but it has potentially very little to do of the training. So we're trying to understand how experts look at medical images from a fine-grained perspective, in hopes of improving training in the future, getting to understand what makes somebody an expert, and hopefully reduce medical error. So we can apply the same kinds of analysis that I have been showing you. So here we have three groups of subjects that are low, intermediate, and high accuracy in their detection performance. Now, this is not a perfect correspondence, but you can roughly think about them as naive subjects, radiology residents, and attending radiologists, okay? And we have them look at images with a range of difficulties, which are ranked from 1 to, which would be very subtle images. 1, 2, 3, 4, and 5 would be the most obvious nodules. Now, the nodule is indicated with a dotted circle in each of the images, and we can again find the consistently versus inconsistently fixated regions across observers, and we can draw scan paths, and we can identify where the microsaccades happen. And so this would be a bit bigger for you to see. This is a successful detection of a nodule, which is inside of this dotted region. And you can see again that not all fixations contain microsaccades. There are a few here and there. So microsaccades are again in red, but the detection of the nodule is accompanied by microsaccade production. So, and this is a bit bigger. All right, so we apply the same kinds of eye movement analysis that we do in other kind of research. So here we're just simply looking at basic microsaccade statistics. We're looking at main sequence plots. So we're plotting the velocity, the peak velocity of the microsaccade versus the magnitude. And these are our three groups of low, intermediate, and high accuracy. And at the bottom, we're plotting the distribution of microsaccade magnitudes. The main point of this slide is that there are no fundamental differences between the dynamics of the three groups. So every group is basically producing the same kinds of eye movements. Now, how they allocate them, that may be the difference. So let's look at this a little bit more in detail. We're looking at the fixation rates for each of the groups, and that for correct versus incorrect trials, in and out refers to inside versus outside the window where the nodule is, the target window. And but what's interesting is what happens here on the right graph. So I want you to see how we have a difference in the correct versus incorrect trials. You can see that consistently for every group of participants, we're producing more microsaccades inside than outside the target area in the case of correct identifications. Okay, So again, this is work in progress, but I have one more graph to show you, which is to demonstrate that how important it is to look at this analysis from a fine-grained perspective, because here we're looking at the numbers of microsaccades over each in that the three groups, but if we now split them, the groups, by the type of images, so we're going here from to very obvious images, you can see that for the naive subjects in blue, basically their production of microsaccades doesn't change. They don't really know what they're doing, so that they just stay flat. They're guessing throughout. A little bit of a trend for the intermediate group, but especially for the high accuracy, this would be the attending radiologists, you can see that they don't really produce a whole lot of microsaccades when the image is obvious. In fact, they find it right away, so they don't really linger there. But as the image difficulty increases, so does the number of microsaccades. And there we have a big difference for the extremely subtle images. All right, I've just been told that I have 10 minutes to go, probably less now, but I want to tell you master of the time. And so what Rubens does, he takes a look at Titian's paintings and he's like, well, I'm going to make my own versions. And he does. So this is The Rape of Europa by Titian and by Rubens. You can see that the color palette changes, but everything else, it's almost pixel by pixel, is replicating the painting. It's like copy paste. But now, this is very interesting because at this time, Rubens was 50 years old. He was at the peak of his artistic skill. And so, why was he copying Titian? As I told you, Titian was considered the grandmaster. And so by copying Titian, his art historians think he's not really trying to learn from Titian. He's trying to show that he can do it better than Titian. He can do it just as well and even better. So it is very interesting when you see very close copy-paste situations with Rubens, but even more so when he introduces differences. So this is Titian's Adam and Eve, and that is the famous scene from Genesis, where Adam is Eve is getting the apple, and Adam here is trying to stop her, and we have the serpent at the tree. So anyway, that's Titian's version, and this is Rubens' version. I think it's a lot better, but it's also a lot different. Okay, so first off, so let's talk about the things that are the same. Eve is basically the same in both paintings. Now, Adam changes a lot. In Titian's version, he's like, "Hey, don't touch me," but in Rubens's version, he's like trying to, what are you doing? Think about it. Think about what you're doing. So he's a bit warmer, more like a. All right, so it's a different composition. All right, so so Adam is a completely different guy. There's of course, being Rubens, we have more flesh, more muscle, more cellulite, and so on. Another big difference. Can anybody see it? Yes, there's a red parrot. Now, there are books, tomes that have been written about that red parrot. Now, some people say that the red parrot is there to balance this fox down here. And but there's also symbolism associated with the parrot, because the parrot means redemption. The parrot actually symbolizes the Virgin Mary. Don't ask me, but apparently I'm told the reason is that the parrot is a miraculous bird because he can speak, and Mary had a miraculous child, so there you have it, the parrot. Now, so that's interesting and all, but There's something else to me as a vision scientist that is interesting about that parrot, and is that that parrot is equiluminant. So as much as with Monet's sun, the parrot doesn't have a luminance contrast with the background. There's chromatic contrast, but not luminance contrast. And if we make the scene black and white, the parrot basically disappears. Now, this is not true of other parrots of the time period. And given the parrot symbolism, at this time, there were a lot of paintings of the Garden of Eve, and a lot of these paintings contain parrots. And we have analyzed those parrots, and they're not equiluminant. They have a lot of contrast, both chromatic and luminically. So I want you to try, let's see if the projector again cooperates, but look at Eve's eye as precisely as you can, and see if the parrot blends with the foliage. It's happening for me right now. Yeah. So, you may require a bit of careful fixation, and that, but the parrot, upon fixation, it blends, and that the color diminishes and so on. Actually, if you have the opportunity to go sometime to El Prado Museum, you actually have both paintings side by side, the Titian version and the Rubens version, and I can confirm that the parrot disappears in real life. All right. So, okay, so we decided to see if microsaccades, again, were related to the fading of the parrot. And if you remember this kind of graph, we have the same kind of relationship as we had before for a contrived Gabor patch and for Monet's sun, right? So again, this is a type of Troxler fading, and the microsaccade production is generating the perceptual alternation dynamics. All right, so back to what Rubens was doing. So we've talked about a lot of obvious differences between the two paintings, Adam, the parrot, and so on. There's something else that changes between the two paintings, and is the gaze of the main characters. So I'll switch to here. In Titian's version, you can see that, well, Eve is looking at the apple. She's actually looking at the apple in both versions. That never changes. She's apple obsessed. Adam is looking at Eve in Titian, and that sorry. I meant to say you cannot see very well here, but Adam is actually looking at the serpent, and the serpent is looking back at Adam. They're sort of like challenging each other. All right, and but in Rubens's version, Adam is clearly looking at Eve's face, and so is the serpent. Even the parrot is sort of like tilting in that direction. Okay, so we've talked a lot about attention, and one of the forms of attention is joint attention, which is paying attention to what other people are paying attention to. Like if I go like that, people tend to orient themselves to where I'm pointing at. Well, Rubens is triangulating the gazes of the characters to point to Eve's face from all of these different directions. And we can actually measure that by collecting the scan paths and then producing the corresponding heat maps, which I'm going to show you in a minute. Already you can see this is from one individual participant. See how scattered the scan path is in Titian's version, and how it becomes a lot more concentrated for the Rubens version, right? And if we collect these scan paths for subject after subject after subject, and we average them in scan paths, then you see that Eve's face is much more of a target of fixation in Rubens' case than in Titian's case. Now, a lot, again, has been written about Rubens' version of Titian's original, and something that is said about it is that there's a lot more life, a lot more motion in the Rubens painting. And I can't help but wonder if that has to do with the appearance and disappearance of the parrot as you look at the painting. And in fact, one prime way to look at at the painting in which the appearance and disappearance of the parrot becomes most obvious is by looking at Eve's face, which is exactly the place where Rubens wants us to look at. Thank you.